We're going to be talking about polymer crystallization and specifically how branching will affect your melting point. So we kind of talked about last time about the driving forces to crystallize a polymer. So again, it goes back to our use free energy. It's these at lower temperatures, T less than Tc, we have this gain in favorable enthalpic interactions. So H decreases because of non-specific interactions, H bonds, van der Waals, etc., but we lose our conformational entropy. Delta S conformation decreases, so this becomes basically more positive, and that is due to folding into this lamella structure. So again, the chain folds into this lamella. The size here is about 10 nanometers, which is about 10%. Usually your polymer is about 1,000 angstroms or so, or even more. So you'll fold these chain lamellar structures, you extend, so we lose our conformational entropy compared to our mixed state. But again, we have this gain in these non-specific or specific intermolecular interactions. So there's that thermodynamic driving force to line chains. When we're at below our temperature, we form, again, this lamella structure. And really, we're going to form, essentially, we're going to see this hierarchical structure. So it's really beautiful. We're going to go from basically some structure or some order at the angstrom, nanometer, and then micrometer length scale with spherulites. And we'll look at spherulites in a second. So again, lamella structure, basically these chain folds, only a fraction of their extended length. Again, usually about 10 nanometers or like 10%. And it basically allows those monomers to interact via those intermolecular bonds. You could then define essentially crystalline, kind of structure. And actually, typically, especially for polyethylene, it'll appear as like a close packed. Actually, it appears as an orthorhombic structure for polyethylene. But you'll have basically the same unit cells like we've seen in material science. So FCC, BCC, HCP, orthorhombic, triclinic, monoclinic, et cetera. So you could kind of derive basically some of these similar unit cells once you have this crystalline structure. So again, this is what we're talking about a hierarchical structure. So polymer crystallization will have some structure at all these different length scales. So at the angstrom length scale, we have, again, short range order due to bonds. Then when we crystallize, we have, again, this nanometer order, this long range translational order due to the lamella. And then we're going to talk about spherulites, a really cool structure. And then those occur at the micrometer length scale. So again, it's this hierarchical structure, and it's a really cool kind of procedure, and actually really beautiful. And actually, I'm going to go ahead and give you a sneak preview before we get into spherulites. So again, this is the hierarchical structure. We'll look at that in a second. But these are our beautiful spherulites under a polarized light microscope. So you can see kind of these different, beautiful colors. It's called also like the Maltese cross kind of structure. And it's due to kind of this birefringence, this change in the refractive index from these polymer chains. And so here you can again see these different structures. So at the angstrom level, you have the crystal structure. At the nanometer length scale, you have, again, these lamella, and then you stack these kind of lamella, and they extend. These lamella extend and they grow basically cylindrically or spherically. They branch out and they kind of stack. And they form the spherulite. But more on that a little bit later on. So let's go back to our lecture, not lecture 9. You're masters of lecture 9. You know self-assembly. So again, we are semi-crystalline. So there's going to be parts that are going to be in the disordered phase. So they're not going to be able to kind of stack. So you'll have some lamella and then some region here, and then maybe some lamella here, and maybe some lamella over here. But there's going to be some regions in here that are not going to be able to kind of fold and stack, because again, we can never get to this perfect structure of just fully aligned chains because of that cost in conformational entropy. So we're going to have multiple regions which are folded and disordered together. So it's going to be this hierarchical structure. Again, there's going to be some amorphous region that has a TG. There's going to have some crystalline region which is going to have a TM in semi-crystalline materials. Amorphous polymers will not have any of these TM regions. So let's think about how branching can depress the melting temperature or affect essentially this packing. So we've been talking about the driving force for crystallinity is the ability of chains to pack close so we can maximize these non-specific interactions. But what happens if I have a polymer like polystyrene, which, for example, actually, just for your information, is fully amorphous. So this is polystyrene, our old friend, PS. This is an amorphous polymer. So this is not going to have any TM or crystalline regions or lamella. Why is that? Well, this phenyl group makes it really, really difficult to kind of pack. So that's one reason as well. But for polyethylene, we know I could have low density polyethylene, which has lots of branches, and I could have high density polyethylene, which has much fewer branches here. So which of these is going to have a higher driving force, or it's going to have a higher melting temperature? Well, we know it's going to be not LDPE, it's going to be our high density polyethylene because they can stack closer together, fewer branches. When we have these branches, basically they're going to kind of push away, and we're not going to be able to stack as efficiently. So if we can't stack as efficiently, if we can't basically gain in these favorable non-specific or specific enthalpic interactions, then there's going to be less driving force to crystallize. So that is going to be one of the key kind of concepts here in terms of the driving force to crystallize and whether your polymer is, and how that's going to affect the degree of polymerization, or the degree, of crystallinity. So the way that there's also a really, really cool method in terms of how polymers will incorporate these branches, or basically these defects. So all polymers, all materials, metals, they all have defects, and every material has defects, just like people. Everyone has some defects. But polymers have a really interesting way of how to incorporate, because even in high density polyethylene, there are branches, and there's ways that you can incorporate these branches into your structure in order to kind of, again, increase your degree of crystallinity depending on your processing routes. So it's not only, again, it's this, there's kind of two components here. We have the thermodynamic side of things in terms of what's going to crystallize, or the degree of crystallinity, but we also have the kinetic aspect too. So we have to consider both. And when I say kinetics, I'll also kind of use this term, what is the processing history of a polymer? And we're going to see an example of how this processing history, how the polymer is processed, can really vastly affect the properties. We've already seen an example of this in our degree of polymerization in our lecture 2, where if you were either Ziegler-Natta or you were free radical catalysis, it changes essentially the number of these branches. So let's take a look at one way processing can affect the properties of these polymers. So if I quench, if there's a high degree of undercooling, so if I put my polymer directly from the melt into kind of liquid nitrogen, these branches are going to be frozen or incorporated into the crystalline structure. So there's going to be there's basically even more defects. So the polymer basically doesn't have time when it's in the melt. So here's my before the melt. It doesn't have time if I quench. So quench, which means cool quickly, very quickly. It's not going to be able to kind of, in this kind of structure, there's still going to be these branches here. And we're going to see a better schematic in a second. But if I cool slowly, the branches can sometimes, the polymer will exclude these branches from the crystalline region. So if I cool slowly instead, so slow, the polymer can kind of look like this, and the branch regions can kind of be like, it'll kind of exclude some of these branches. Again, there's always going to be some defects in here. So it'll form basically from the crystal structure from the lamella, and it'll basically this disordered fringe here. So that's what we're talking about here, this disordered fringe. Again, this is the balance or the consideration we have to kind of think about between kinetics and thermodynamics. So if branches are part of this lamella region, the melting point will change as a function of the number of these defect sites. And actually, we could see this right here. So where X is basically the mole fraction or number of these non-crystallizable units, i.e. the number of branches or defects in your material. So you can see here, this expression makes sense because the melting temperature, Tm, as a function of X, is going to decrease as more branches are introduced, as X increases, because this inverse relationship here. Again, ore is more difficult. As we have more branches, it's going to be a smaller crystallite size. Again, the branches push apart these, so I have less of these intermolecular interactions that are kind of closer together, and it's going to basically there's going to be a lower temperature is going to be required for crystallization, because again, there's not this large enthalpic driving force here. So we're going to need to decrease T even lower. So here, my TC, my temperature for crystallization is going to be higher than the TC for this one. Because again, I need lower T, I need more basically enthalpic driving force, more thermodynamic driving forces to kind of push us towards that crystalline region. Also, if you have low molecular weight, that will also affect the melting point, not only due to the number of these interactions, but your chain ends. So if I have a polymer like this, short polymers instead of long polymers, there's more chain ends here at low molecular weights, and they can also act as impurities as well. So you can kind of see this whole concept shown here. So LDPE versus HDPE. So if I have slow cooling here, I can, again, exclude some of these branches from my perfect structure. If I quench, then I'm just stuck. Look at all these branches are there in my crystalline region. They serve as defects. They push apart, and we can't crystallize as efficiently. So next time we are going to get into a discussion of spherulites and how these structures form and really the beauty of them. And we'll look at some again. You already saw a little bit of a highlight for some cool pictures of spherulites, but again, we'll appreciate kind of this hierarchical structure and order, and then we're going to get into some derivations. I'm sure everyone's excited. So I'll see you all next time. Thanks. Bye.